ഇന്ന് CV കണ്ടുപിടുത്തത്തെക്കുറിച്ചും ഏറ്റവും ലേറ്റസ്റ്റ് ആയിട്ടുള്ള CV രാമന്റെ റീസെന്റ് ട്രെൻഡ്സ് ഇൻ റിസർച്ചിനെ കുറിച്ചും ഒക്കെ നിങ്ങളോട് ഷെയർ ചെയ്യാൻ പോകുന്നു. ഒരു വലിയ പൈതൃകമുള്ള ഡിപ്പാർട്ട്മെന്റ് ആണ് ഫിസിക്സ് ഡിപ്പാർട്ട്മെന്റ്. പ്രത്യേകിച്ചും CV രാമന്റെ സ്റ്റുഡൻ്റായ CS വിശ്വനാഥൻ, അദ്ദേഹമാണ് നമ്മുടെ ഏറ്റവും ആദ്യത്തെ ഹെഡ്. ഇന്നും നമ്മളത് എല്ലായിടത്തും നമുക്ക് ഉപ്പുപ്പായ്ക്ക് ഒരു ആനയുണ്ടെന്ന് പറയുന്ന പോലെ നമ്മൾ പറയുന്ന ഒരു കാര്യമാണ്. അതൊരു ലെഗസിയാണ്. ആ ലെഗസി ഉണ്ട് ഞങ്ങൾക്ക്. ആ ലെഗസിയിൽ തുടർന്ന് വന്ന അധ്യാപകരാണ് അരുൾദാസ് സാറ്, അരുൾദാസ് സാറിന്റെ പ്രിയ ശിഷ്യനായ ഹുബർട്ട് ജോ സാറ്. അങ്ങനെ ആ ലെഗസിയിലുള്ള ഒത്തിരി ആൾക്കാർ ഈ ക്യാമ്പസിലുണ്ട്. അപ്പൊ അങ്ങനെ അവരിൽ നിന്ന് കേൾക്കുക, അതാണ് ഇതിൻ്റെ ഉദ്ദേശം. ജോ സാറ് കുറിച്ച് പറയുകയാണെങ്കിൽ തന്നെ ഈ യൂണിവേഴ്സിറ്റിയിൽ ഏറ്റവും കൂടുതൽ റിസർച്ച് പബ്ലിക്കേഷൻ ഉള്ള ആള്, ഏറ്റവും കൂടുതൽ സൈറ്റേഷൻ ഉള്ള ആള്. ഈവൻ നിങ്ങൾ റാങ്കിങ്, വേൾഡ് റാങ്കിങ് എടുത്ത് നോക്കിക്കഴിഞ്ഞാൽ നിങ്ങൾക്ക് മനസ്സിലാവും. സോ ഈസ് എൻ ഇന്റർനാഷണലി റെക്ലെയിംഡ് ഫിഗർ. അപ്പൊ അതുകൊണ്ട് തന്നെയാണ് ഡിപ്പാർട്ട്മെന്റ് ലെഗസി തന്നെ ആകണം ആദ്യത്തെ ടോക്ക് എന്ന് ഞങ്ങൾ തീരുമാനിച്ചത്. സാറിനോട് ചോദിച്ചപ്പോൾ കുട്ടികളാണ് ചോദിച്ചത്. അപ്പോൾ ഉടനെ തന്നെ സാറ് പൂർണ്ണ സമ്മതം, കുട്ടികൾ എന്ത് പറഞ്ഞാലും പൂർണ്ണ സമ്മതത്തോടെ നിൽക്കുന്ന ഒരു അധ്യാപകരാണ്. അപ്പൊ പൂർണ്ണ സമ്മതം തരികയും സാറ് ഈ ടോക്ക് എടുക്കാൻ തരാമെന്ന് പറയുകയും ചെയ്തു. അപ്പൊ നിങ്ങൾ സാറുമായിട്ട് ഇന്ററാക്ട് ചെയ്യുക, ശരിക്കും പറഞ്ഞാൽ ഫ്രണ്ട്ഷിപ്പ് ഉണ്ടാക്കുക. കുറെ അറിയാവുന്ന ആൾക്കാരിൽ നിന്ന് കുറച്ച് ഫ്രണ്ട്ഷിപ്പ് ഉണ്ടാക്കിയിട്ട് ഇവിടെ നിന്ന് പോവുക എന്നുള്ളതാണ് ഈ മീറ്റിങ്ങിന്റെ ഉദ്ദേശം. സൂപ്പർ 30 എന്ന് പറയുന്ന സിനിമ നിങ്ങളെല്ലാവരും കണ്ടിട്ടുണ്ടാവും. 30 കുട്ടികളെ ട്രെയിൻ ചെയ്യിക്കുന്ന ഒരു കഥയാണ്. എനിക്ക് നമ്മുടെ ഡിപ്പാർട്ട്മെന്റിൽ തന്നെ 45, 32, 70 കുട്ടികൾ അല്ലാതെ ഉണ്ട്. അതിൻ്റെ കൂടെ ഒരു 30 കുട്ടികൾ. നിങ്ങൾക്ക് അലൂമിനയും ഉണ്ടാവും. കഴിഞ്ഞ സൂപ്പർ 30 കുട്ടികൾ വരുന്നുമുണ്ട്. അപ്പൊ ഇവിടെ ഒരു സൂപ്പർ 30 ഒരു അലൂമിനൈ ഉണ്ടാകുന്ന ഒരു അവസ്ഥയാണ്. അപ്പൊ തീർച്ചയായിട്ടും നല്ല കുറെ ഗുരുക്കന്മാരെ ഇവിടെ കിട്ടും. നിങ്ങൾ അവരുമായിട്ട് ഇന്ററാക്ട് ചെയ്യുക. ഒരു ഒഫീഷ്യാലിറ്റിയുടെ പേരിൽ ഓൺ ബിഹാഫ് ഓഫ് ഡിപ്പാർട്ട്മെന്റ് ഓഫ് ഫിസിക്സ്, യൂണിവേഴ്സിറ്റി ഓഫ് കേരള, ഐ എക്സ്റ്റെൻഡ് വാം വെൽക്കം ടു ഹുബർട്ട് ജോ സാർ ടു ഗിവ് ദി ഫസ്റ്റ് ഇൻവൈറ്റഡ് ടോക്ക്. വെൽക്കം യു സാർ. ഫോട്ടോ എടുക്കുന്നത് അവിടെ വന്ന് എടുക്കണ്ടേ? ഞാൻ ഫോട്ടോ എടുക്കണ്ടേ പോലും? ഇത് രോഹിത്താണ്. രോഹിത് നല്ലൊരു ഫോട്ടോ എടുത്തു തരും. പ്രത്യേകം പരിചയപ്പെടുക. നമ്മുടെ ചിത്രങ്ങളൊക്കെ മനോഹരമാക്കുന്നത് ശരിക്കും ഒരു ഫോട്ടോഗ്രാഫറിന്റെ കഴിവാണല്ലേ. ഇപ്പൊ രോഹിത്തിന്റെ മനസ്സിൽ ടെൻഷൻ ഉണ്ടാകും, എന്തായാലും ഫോട്ടോ പതിഞ്ഞിട്ടുണ്ടാവും അല്ലയോ അല്ലേ? ഇനി ഞാൻ പറഞ്ഞില്ലേ, നമ്മളിവിടെ എല്ലാവരും ഒരു ഫ്രണ്ട്ലി ആയിട്ടുള്ള ഒരു അറ്റ്മോസ്ഫിയർ മെയിൻറ്റെയിൻ ചെയ്യാൻ ശ്രമിക്കുക. നമ്മുടെ ഏറ്റവും വലിയ സ്ട്രെങ്ത് ഞങ്ങളുടെ ഡിപ്പാർട്ട്മെന്റിലെ 12 അധ്യാപകരാണ്. ആ 12 അധ്യാപകർ എല്ലാ കാര്യത്തിനും ഒറ്റക്കെട്ടായിട്ട് നമ്മുടെ കൂടെ നിൽക്കുന്നതുകൊണ്ടാണ് ഇതെല്ലാം പോസിബിൾ ആയിട്ടുള്ളത്. ജവഹർ സാറുണ്ട്, ദീപ ടീച്ചറുണ്ട്, അശ്വതി ടീച്ചറുണ്ട്, ദിവ്യ ടീച്ചറുണ്ട്. എല്ലാവരും ഇവിടെ ഉണ്ടായിരുന്നു. എല്ലായിടത്തും നിങ്ങൾക്ക് പോയി പരിചയപ്പെടാം, കാണാം, മിണ്ടാം. എല്ലാവരും വളരെ ഫ്രണ്ട്ലിയാണ്. നിങ്ങൾ തീർച്ചയായിട്ടും പരിചയപ്പെടുക. യൂണിവേഴ്സിറ്റി ഓഫ് കേരള ഒരു റിസർച്ച് സെന്റർ കൂടെയാണ്. ഇന്നല്ലെങ്കിൽ നാളെ നിങ്ങൾ ഞങ്ങളെ കാണേണ്ട ആൾക്കാർ തന്നെയാണ്. അപ്പൊ അതുകൊണ്ട് തന്നെ ഒരു ഒഫീഷ്യാലിറ്റിയുടെ പേരിൽ എല്ലാ അധ്യാപകരെയും ഞാൻ ഈ വേദിയിലോട്ട് സ്വാഗതം ചെയ്യുന്നു. അതുപോലെ തന്നെ സവിത ടീച്ചർ പുറയിലുണ്ട്. സവിത ടീച്ചറിനെ പ്രത്യേകം വെൽക്കം ചെയ്യുന്നു. അതുപോലെ തന്നെ ഇവിടെയുള്ള ടീച്ചിങ്, നോൺ ടീച്ചിങ്, അത് ഓഫീസ് സ്റ്റാഫ്, അവരൊക്കെ ഒത്തിരി നിങ്ങൾക്ക് വേണ്ടി പ്ലാനൊക്കെ ഉണ്ടാക്കുന്നുണ്ട്, സർട്ടിഫിക്കറ്റ് ഉണ്ടാക്കുന്നതിന്റെ തിരക്കിലുണ്ട്. ഇതിന്റെ പുറയിൽ നിൽക്കുന്ന കുറേ പേരുണ്ട്. ഈവൻ PGയിലെ SLA ഉള്ള കുട്ടികളുണ്ട്. അവരെ എല്ലാം ഇതിലോട്ട് വെൽക്കം ചെയ്യുന്നു. പിന്നെ ഇവിടുത്തെ ചീഫ് ഗസ്റ്റ് സൂപ്പർ 30 ആണ്. നിങ്ങൾ 30 പേര് പോയി കളയരുത്, ഫുൾ പ്രോഗ്രാമിന് ഇരിക്കണം. പിന്നെ ഒരു ചെറിയ ആഗ്രഹം, നമ്മുടെ ഇവിടുത്തെ ഡയറക്ടർ GM നായർ സാർ പറഞ്ഞൊരു ആഗ്രഹം ഇതാണ്. ഇത് ഒത്തിരി ബുദ്ധിമുട്ടി യൂണിവേഴ്സിറ്റി ഉണ്ടാക്കിയൊരു ഫെസിലിറ്റിയാണ്. അത് കാണുന്നതിൻ്റെ ഒപ്പം നിങ്ങൾ ഇത് നന്നായി മെയിൻറ്റെയിൻ ചെയ്യാൻ, നിങ്ങൾ ഇട്ടിരിക്കുന്ന കസേര ഇറങ്ങി പോകുമ്പോഴും ആ പൊസിഷനിൽ തന്നെ ഇടാനായിട്ടും, ഈ ഫെസിലിറ്റി അതിൻ്റെ മനോഹാരിതയിൽ തന്നെ കീപ്പ് ചെയ്യാനായിട്ടും നിങ്ങൾ ശ്രമിക്കണമെന്ന് ഞാൻ പറയുകയാണ്. ഒരിക്കൽ കൂടെ ഇവിടുത്തെ ക്ലിഫിന്റെ ഡയറക്ടർ GM നായർ സാറിന്, ഇവിടുത്തെ ഡെപ്യൂട്ടി ഡയറക്ടർ സുബോസ് സാറിന് ഈ ക്ലിഫിന്റെ ഈ വേദി നമുക്ക് തന്നതിന് നന്ദി പറഞ്ഞുകൊണ്ട് എല്ലാവരെയും വെൽക്കം ചെയ്തുകൊണ്ട് പ്രോഗ്രാം തുടങ്ങാം. അടുത്തതായിട്ട് അരുന്ധതി പറയുമല്ലോ അല്ലേ? ശരി. Thank you.
Here we welcome Dr. Hubert Joseph, Associate Professor, Department of Physics, University of Kerala. The one who is going to handle the session for us does not owe an introduction, as he is well recognized as one of the prominent faculty of our department. And he is still known for achievements and in the field of research and academic career. So I introduce you, sir, to take the stage.
So good morning to everybody. I take this opportunity to thank the head of the department and other faculty members to give the opportunity to give the talk spectroscopy. Spectroscopy. I just like mention from the basic to some recent trends also. This word is by Raman. I propose this evening to speak to you on a new kind of radiation or light emission from atoms and molecules. So this is by Raman in March 16, 1928. So Raman words. Okay. Raman, the era 1988 to 1970. One of the indigenous scientific minds of the 20th century. Okay, next. Okay. Now, his name was C.V. Raman Sandrasekara Venkat Raman. His name is Sandrasekara Venkat Raman. He was born in Chirapalli, Tamil Nadu. He's a gold medalist in physics in the year 1907. Alma Mater of Presidency College, Chennai. First Indian to receive Nobel Prize, 1930, by Raman scattering. Bharat Ratna, the year 1954. Lenin Peace Prize, 1957. His early works on optics and acoustics, later fascinated by scattering of light. He was established the Raman Research Institute, which is situated in Bangalore, after independence in Bangalore. Okay. See, he was born in the child house. And just go to this, I think there is no electricity. Even without electricity, he was the recipient of the Nobel Prize. So money is not the matter. As a young physicist, you can do a lot of things. Money is not the matter. And the facility, luxury life is not the matter. So even without a light or electric light, so he received a Nobel Prize, so prestigious prize here in India. Okay, so his house is his child was very small house. That's why I just bring this photo in order to give the enthusiasm to you. So I have no money. We have a poverty. We are very poor. We cannot do anything. So don't feel like that. So you cannot do anything. You can do anything if you have a will to do. So you can win a Nobel Prize. Okay. Next. So Raman used a very simple instrument. Spectroscopy is nothing but interaction of radiation with matter, electromagnetic radiation. He used a simple spectrometer. He used sun as the source, telescope as a receiver, and eye as a detector. No specific instrument. Very simple instrument. So using the simple instrument, he invented the Raman scattering. Okay. Now, this is a whole electromagnetic radiation. So gamma ray, X-ray, UV, visible IR, microwave, NMM is radio frequency. So this is a whole regions of electromagnetic spectrum. So different regions of the electromagnetic radiation gives the different information of the molecule. So gamma ray, you might have studied Moscow spectra. X-ray for X-ray single crystal structure determination, X-ray is normally used. UV, so this is electronic level transition, electronic spectra. IR is a vibrational spectra, and visible is also a electronic spectra. Then microwave is a rotational spectra. Again, ESR is again a microwave spectra, microwave. Then NMR is a radio frequency. Okay, radio waves. So the different regions of the electromagnetic spectra, electromagnetic region gives the different information about the molecule. Now, see, I'm giving that. So we know that molecules have different energy levels, rotation levels, vibration levels, electronic levels. The separation between the rotation level is of the order of say 1 to 100 or 1 to 300 wave number. Separation between the vibration level is of the order of 1000 to 3000 wave number. Separation between the electronic level is of the order of say 10 to the power 6 wave number. So here, see, rotational level transition gives the rotational spectra that is fall in the microwave region. Vibration level transition fall in the infrared spectra, that is infrared region. So it's called infrared spectra. So electronic level transition gives in the visible or microwave region. For IR region, sorry, UV visible region, UV, ultraviolet and visible region. So here, why I am giving this slide is, see, vibration, Raman spectra is a vibrational spectra. So the transition is within the electronic level. Okay. So the transition just see the ground electronic level. So here is the transition. See, when the atoms or molecules, the ground state after absorption of energy goes to the virtual level. Okay. That virtual level is below the first excited electronic level. Whereas in the case of other fluorescence, all these things, it can, after absorption energy, go to the next excited electronic level. Okay. So that is ground level. Ground is excited. So the dark line is a ground electronic level. Again, the dark line is a first excited electronic level. So within the electronic level, there are number of vibration level as well as within the vibration level, there are number of rotation level. So vibration, this Raman spectra is the vibrational spectra. So we are talking about the vibration level transition. Okay. Next. Now, the history of Raman spectroscopy, you know that in 1923, inelastic light scattering is predicted by A. Schmegel. In 1928, C.V. Raman discovered that small changes occur, the frequency of a small portion of the light scattered by the molecules. The changes reflect the vibrational properties of the molecule. Raman was awarded Nobel Prize in 1930. So in the first 12 years after this discovery, about 1,800 research papers were published and about 2,500 compounds were studied. So after the discovery of Raman, about 12 years, only 1,800 research papers were published. That means there is a hurdle is there. Raman signals are weak signals. So Raman used the sun as a source. After that, they used the mercury from the mercury vapor using a filter. So 435.5 nanometer and the blue color and 235.8 nanometer in the UV region. UV sources from the mercury vapor lamp. They have separated using a filter. That source is used. They have used earlier. The problem is that the brightness, the brightness available per unit area is very small. So you need a large quantum sample and you have to give more exposure time. So it is very difficult to get the Raman signal. So you know that the scattering efficiency is proportional to the fourth power of frequency. But when the frequency increases, normally the scattering increases. But the problem is, for recording the molecules, because of the fluorescence problem, it is very difficult to get the Raman spectrum. So in order to get a good Raman spectrum, low frequency is preferred. Because when you use the low frequency source, the scattering efficiency weak. So it is very difficult to get the Raman signals. So that's why, say, after this 12 years, only 1,800 papers, only 2,500 chemical compounds was, say, studied. Now, see, this is a person, Charles Town. So Nobel Prize winner, he was invented the laser. I got the opportunity to meet Professor Townsend at Boston. Now, in the year 1970s, laser made much more practical. So you know the property of laser, it's a high intensity, low line width, okay, high power. There are so many lasers so invented after that. So this Raman scattering becomes more powerful. So after the invention of the laser source, so they used a laser source. So more compound has been studied, more number of papers have been published. Okay. So now if you use this NAR laser, you can avoid the fluorescence problem. Whatever be the compound, whatever be the color of the compound, you can get the Raman spectra after the discovery of the laser only. Before that, it's very difficult to record even a colored sample. So when you go through the earlier book, only transmitted sample is alone recorded. But nowadays everything is changed. Even a black samples can be able to record the Raman spectra. Now, so different laser sources are available. Argon ion, 488 blue color, same source you can see 514.5. So green, krypton laser, helium ion laser, diode laser, NDAG laser. So depending on the sample, you can vary the laser source, you can get the Raman signal. Now, we know that, so scattering, when an electromagnetic radiation interacts with the molecule, what will happen? Some radiation may be scattered, something may be absorbed, something may be reflected, something may be transmitted. Okay, these are the properties of light. So when electromagnetic radiation interacts with the molecule, some radiation may be reflected, some radiation may be transmitted, some radiation may be absorbed, some radiation may be scattered. So the scattering is nothing but absorption and emission. So absorption of one photon and emission of another photon. So this is a two-photon process. Absorption of one photon and emission of another photon. So now, so when an electromagnetic radiation, just to quantify that, see how the intensity varies. If 10 to the power 3 photons, we know that when an electromagnetic radiation interacts with a molecule, the radiations are scattered. The scattered radiation contain the same incident frequency. In addition to the incident frequency, some higher frequencies are there, some lower frequency lines are there. That is a higher frequency called the anti-Stokes line, lower frequency called Stokes line. So this is a Raman effect. So now what is quantify the intensity? So when assume that if 10 to the power 3 photons are incident on the molecule, 1 photons will be scattered elastically. That means, Rayleigh scattering is elastic scattering. There is no loss or gain of energy. If 10 to the power 6 photons are incident on the molecule, 1 photon will be scattered inelastically with the frequency lower than the incident frequency. That is called Stokes line. If 10 to the power 9 photons incident on the molecule, one photon will be scattered inelastically with the frequency higher than the incident frequency. What I am quantify that the Raman signals are big signals compared to Rayleigh scattering. Whereas when you compare this Stokes and anti-Stokes line, this intensities are lower, but this than the Stokes line, than the Rayleigh scattering. The intensity variation I will explain later. Okay. Anyway, the intensity of these scattered lines will be lower, very small. Okay. Now, this center line is a Rayleigh line. Right side, the frequency, higher frequency, that is anti-Stokes line. So when you just study the molecule, you can get both Stokes line and anti-Stokes line. Normally, suppose you are using any wavelength, any source exciting radiation, that wavelength will be taken as a zero. That is converted to wave number, that will be zero. So about that, we got recorded, that will be a shift you'll get. So same shift in the higher frequency region and same shift in the lower frequency region also. But just see the right side is a frequency, higher frequency. That just see the lines. There are some lines, same separation, shift same, left side, right side. That is anti-Stokes line. Left side, this same frequency, but this is Stokes line. But just see the intensity of these Stokes lines are more than the intensity of the anti-Stokes line. But the Rayleigh line is much more intensity. Okay, so simple. So when an electromagnetic radiation interacts with the molecule, the dipole may be created. So there will be a separation of charge and occurs. So positive charge attracts electrons and negative charge attracts nucleus. There will be a separation of charge centers. The induced dipole occurs. So the induced dipole P is directly proportional to strength of the electric field of the electromagnetic radiation. Or we can say P equal to alpha E, or alpha is a polarizability. That you can study all these things. So P is induced dipole moment. Now, I'm just talking, this is a classical theory. Just I'm giving I'm not going to discuss about the derivation, all these things. Just see the last line. So when an electromagnetic radiation interacts with the molecule, there are three components. One is same frequency, that is nu zero, that is Rayleigh scattering. The other frequency, nu zero minus nu m, that is frequency lower than the incident frequency, that is Stokes line. The other one, nu zero plus nu m, the frequency higher than the incident frequency. So that is anti-Stokes line. So you can see three components. But the classical theory fails to explain the intensity of these lines. But classical theory gives that when an electromagnetic radiation interacts with the molecule, so here there are three components: the same frequency, frequency higher, and frequency lower. Okay, same frequency nu zero, frequency lower is nu zero minus nu m, and frequency higher frequency, that is nu zero plus nu m, that is anti-Stokes. There are three components are there. But what about the intensity? It fails to explain the intensity. So in order to explain the intensity, there will be a quantum theory. Okay. So here, see, I told you, see that just see the intensity center is a Rayleigh line. Right side anti-Stokes, left side Stokes line. See here the levels, vibration levels, V equal to 0 is a ground vibration level. V equal to 1 is a first excited vibration level. Above there is a dot line that is called virtual level. I told you, so the virtual level should be below the first excited electronic level. So when an electromagnetic radiation is on the molecule, so V equal to 0, that means molecule in the ground vibration level. After absorption of energy, it goes to the virtual level. Then after spend some lifetime, it comes back to the ground vibration level, that is the same level, that is called the Stokes, that is called the Rayleigh line. So when V equal to 0, after absorption, they go to the virtual level and comes back to the same level, that is Rayleigh line. In the case of Stokes line, so V equal to 0, molecules normally in molecules, most of the molecules are occupied in the ground state. So after absorption energy, it goes to the virtual level. So virtual level is nothing but it's not the station level, it's only a temporal level. So that level depends on the strength of the electric field of the electromagnetic radiation and the molecule. It varies from molecule to molecule. That depends on the strength of the electric field also. Both depends both the strength of the electric field and the molecule. So when the electric field of the electromagnetic radiation is on the molecule, after absorption, it goes to the virtual level. The condition for the normal Raman scattering is the virtual level should be below the first excited electronic level. When you give more energy, the virtual may increase. Give less energy, virtual may decrease. But it should not cross. It should be just below the first excited vibration level. If it touches the first excited vibration level, that Raman is called resonance Raman, not the ordinary Raman. Okay. So if this should be below the first excited electronic level. Now, see here in the case of anti-Stokes line, see the molecule is originated from V equal to 1 level. The separation between the vibration level is of the order of 1000 to 3000 wave number. At room temperature, that energy, so if you just calculate 3 by 2 kT, that energy is not sufficient to go from V equal to 0 to V equal to 1. The separation between the vibration level, that is about 1000 to 3000 wave number. The room temperature, the obtained energy is not sufficient to go from V equal to 0 to 1 level. So the most of the molecules will be in the ground state only. So the population will be more in the ground state. If there is any temperature, occasionally some molecules may be in the, if some molecule obtain some temperature, if get more energy, then sometimes go to the virtual level. Well, only very limited. But most of the molecules will be in the ground state only. So here in the case of Stokes line, it originated from V equal to 0 level. So the population will be more. Population in the intensity depends on the population. So since it is originated from V equal to 0 level and go to the virtual and comes back to the first vibration level, that means it is an inelastic scattering, or here the molecule takes some energy from the photon, or the photon gives some energy to the molecule. That is a loss of energy to the photon. So that separation is the new young. That is vibrational energy. That is a Raman shift. Okay. So here that varies from molecule to molecule. The vibrational energy level of the molecule is vary from molecule to molecule. Again, the case of anti-Stokes line. So here it is originated from V equal to 1 level, where the population is less. So the intensity is also less. So that is why the Stokes lines are more intense than the anti-Stokes line. Since it is originated from the ground state, the intensity will be more when compared to the anti-Stokes line. Now, so here is V equal to ground state. So this is excited electronic level. So in between, there is a virtual level. So virtual level is only a temporal level. Now, whatever be the spectrometer, it's a basic principle. The source is the sample compartment, wavelength selector, detector. So these are the components of the Raman source. Now, everywhere laser is used. Normally, the Raman spectrometer is called laser Raman spectrometer because we are using a laser source. So it is called laser Raman spectrometer. So you can select any wavelength of laser depending on the sample. You can select, then sample compartment, then wavelength selector. Okay, detector. So these are the essential part of the spectrometer. Now, so if you use this any laser you can use for biological samples. Normally we use the NIR laser, near infrared. So where you can reduce the fluorescence. Normally these biological samples use fluorescence. So we're not able to get the Raman peaks. So in order to reduce or eliminate the fluorescence, NDR laser or NIR laser, 1064 nanometer is more useful. Now this is a simple Raman spectrometer. Okay. Now, see, whatever be the sample, it can be either polycrystalline or gas or liquid or single crystal. Any type of sample, you can record the Raman spectrum. Okay. So this can be, say, compound, whatever the sample. For example, this is our polycrystalline sample. You can just make a pellet, you can take a capillary tube and just fill it tightly. Nowadays, this is not required. Even a place there before that microscope, you can get it. Okay. Earlier, we have used this small capillary tube, fill it packed, tight it, fill it back, tightly packed, you get the good spectra. Then, say, suppose if it is gases or liquid, suppose if the sample is highly hygroscopic, you can just place it, you can evacuate it, you can seal it. So you can place the Raman compartment, you can sample compartment, you can get the Raman spectrum. For example, if you just want to record the single crystal, if you can go a good crystal, you can place in the goniometer. So cut in the form of parallelepiped using a polarization microscope. You can find out ABC axis. You can place the crystal in the goniometer. You can select the direction of incident radiation, selection of the scatter radiation, and you can change the electric vector of the incident radiation. I can change the electric vector of the scatter radiation. So all these things are possible. So you can change. You can, if you just want to find out the symmetry of the molecule, whether the symmetric mode or asymmetric mode, you can able to find out. Just to crystal change the direction of incident light and direction of scattered light and the direction of the electric vector of the incident light, and you can change the electric vector of scattered light. Then you can change. That is a possibility. So you can able to find out the symmetry, whether are asymmetric modes, you can able to find it easily. Now, so what is the information? What are the information? What is the inference? You can get it. How this Raman spectra is getting. So these are the basic things you can know. Okay. You know, there is a molecular vibrations is broadly classified into two. So internal vibrations and external vibrations. Internal vibration normally we state that is stretching and bending or deformation. The external vibration is translations and librations or rotations. Normally, translations or rotation, that is external vibrations, comes in the low frequency region, so below 300 wave number region, and the internal vibrations comes in the above 300 wave number region. Normally 300 to 4000 regions is a rich region. All the internal modes of vibration will be there. And again, stretching we can divide into two: asymmetric stretching, symmetric stretching. Then deformation or bending is again divided into two. That is in-plane bending, out-of-plane bending. Again, in-plane bending is scissoring and rocking. Out-of-plane bending is dragging and twisting. So these are the vibrations of the molecule. So molecular vibrations normally, suppose if you just to prepare the sample, just to record the Raman spectra, you can get some peaks. So from that you can find out what are the functional groups available. You can get it. But the low frequency region is very important for physicists. So there is most of the physical parameters, physical properties are getting from the low frequency regions. Normally we ignore low frequency region. That's external vibes are very, very important. So we just the phase change, you can get the translation and liberational modes. So the low frequency region is very important for physicists. For chemists, normally we people are just to prepare one sample. We just record what are the groups present. We can just identify the molecule for this one. For the high internal modes vibrations. Whereas the low frequency region, so most of the physical parameters, physical properties comes in the low frequency. Okay. Now, just see, we know that everybody knows there are n atoms in a molecule, there are 300 degrees of freedom. Of these, 3 coordinates are used for rotational motion and 3 coordinates are used for translational motion. The remaining 3 and minus 6, normal modes of vibration. In the case of linear molecule, since there is no rotation along the bond axis, only 3 and minus 5 normal modes of vibration. That is again 3 coordinates are used for the translation motion and 2 coordinates are used for the rotational motion. The remaining 3 and minus 5 normal modes for the normal modes of vibration. Okay. So here, so this is stretching. All the bonds on the same direction. This is symmetric stretching. One band is elongated, one compressed. This is asymmetric stretching. So here bending. If all the atoms are moved the same plane, is in plane. If any one of the atoms are moved to the other plane, this is out of plane bending. Okay, so scissoring and rocking. Here wagging and twisting. Scissoring and rocking are the in plane. So here this vibrations on the same plane. So here rocking and twisting, the vibrations are any one out of either perpendicular to board or into the board. So one atom, then that's out of plane bending. Okay. Now you're going to study in carbon dioxide molecule. So there are linear molecule, 3 n minus 5 3 n minus 5 normal modes of vibration. So normally 3 into 3 minus 5. How many? 9 minus 5. Normally 4 modes you can expect it. But say out of 9, n minus 1 stretching modes, 2n minus 4 bending modes are for the linear molecule, 3n minus 5 bending modes for the non-linear molecule. So you can expect 2 stretching modes and 2 bending modes. So here, since the bending mode of carbon dioxide molecule is doubly degenerate, so you can expect only 1 bending mode. That means 2 vibrations having the same frequency. It is called doubly degenerate. So you can expect only 1 bending mode and 2 stretching modes. One is symmetric stretching, the other one is asymmetric stretching. The condition for is one more thing. The condition for getting the Raman spectra, I forgot to take. Okay, 1 minute. So the condition for the equation. Okay, see. So the equation contains dou alpha by dou q. That is there. If dou alpha by dou q equal to 0, that means there is no Raman line. If dou alpha by dou q equal to 0, there is no Raman line. That means there should be a change in polarizability during vibration or rotation. That is a condition for getting the Raman spectrum. So in order to get, so there is a condition. If there is a change in the polarizability, then only it will be Raman active. Otherwise, Raman inactive. So for getting the Raman spectra, the condition for is there should be a change in polarizability during vibration. Okay. So if you see this equation, 1 by 2 dou alpha by dou q. So this bracket is there. So if there is this 0, that means there is no Raman lines. So the condition for Raman line is there should be a change in polarizability. So here, in the case of Raman, there's only one mode, carbon dioxide, only one mode is Raman active. That is symmetric stretch mode alone. The other 2 modes are Raman inactive. Okay. So that's why normally when you're recording the Raman spectra, IR spectra is also recorded. So both are complementary. Even though IR spectra is also a vibrational spectroscopy, so both are complementary. Sometimes one method will give the information, the other method will not give the information. So when you do this Raman vibration spectra, you have to study both Raman and IR is required. That's why. So in this case, the only mode is Raman, only one mode is Raman active, in the case of carbon dioxide molecule, but the other 2 modes are active in the IR spectra. Okay. So you'll get only one mode is Raman active. The symmetric stretch modes are. We just see the symmetric stretch of the asymmetric stretch of the carbon dioxide molecule. Okay. The symmetric stretch of the carbon dioxide molecule. Now symmetric bending of the. So how the molecules are vibrating. Just show you. So this because the symbol 3 atom CO2. You can visualize how the molecules or atoms are vibrating. So this is vibrational spectra. While vibrating, there will be a frequency. Okay. So that you can able to record the spectra. Now I'm just I'll give some more complicated. So these are information. So we know the functional group, different functional groups gives the different frequency region. So from that, when you record the Raman spectra, you can give some bands. So from that, you can easily identify these are the functional groups are there. So the compound is this. You can able to from the internal modes of vibration from say 400 to 4000 wave number. So there are a large number of internal vibrations are there. So you can able to find out from these vibrations, you can easily identify these are the groups are present. So the molecule is this. You can identify from that. Now see. So one more thing is, for example, for C single bond, vibrational frequency depends on the strength of the bond between the atoms and the reduced mass of the system. Nu equal to 1 by 2 pi root of k by mu. Bond strength increases, the frequency increases. Bond strength decreases, frequency decreases. Then mass increases, frequency decreases. Mass decreases, frequency increases. C single bond C 1200 wave number. C double bond C, the frequency changes. C triple bond C, the frequency increases. So you can find out that whether the bond is single bond or double bond or triple bond, that you can able to get it from the Raman spectra. So this is the frequency bond strength increases, frequency should be there. So from we can able to identify. Then whether it is isolated, or it is conjugated, or it is aromatic. So everything, the frequency shift will be there. You can able to find out whether it is isolated or conjugated or aromatic. So that you can able to find out. Now, see, I'm just quickly pass on. I'm taking the benzene molecule. So we know that C6, it's 6, no? There are 12 atoms, 12 into 3 minus 6, 30 vibrations are there. Right? So how the vibrations, you can just visualize. I quickly pass on to how this, so that was designated by Wilson. And just see how the molecules are vibrating. You can just see difference. Quickly, I just pass on that. So this is the notation by Wilson notation. Okay. Just see the molecule, how the molecules are vibrating. There is a small change will be there. So there are 30 vibrations and different. Okay. Now, so that is from the, you can get the information from the Raman spectra, from the, just recall the Raman spectra against some peaks. So from that you can identify the compound. Okay. Now, so some of the applications of the Raman spectra, we just take a diamond. How will you find out which one is pure? It's very difficult to find out the purity of the diamond. If you just record the Raman spectra, if you get only one peak, you can definitely say that this diamond is highly pure. So this is, if you just record the Raman spectra, you get 1332 nanometer, just one peak. If there is any additional peaks, that means there are some impurity. That means you can just find out the purity of the material. This is exactly, you can able to get the Raman spectra. Then again, it is silicon, only one band. Then germanium. So the costly things, material, purity, you can check using the Raman spectra alone. Nothing, no mother. Even though there are some impurity, if there is any small impurity, you can able to get it from the Raman spectra. Okay. So nowadays also this diamond, for diamond purity, Raman spectra is using for the purity checking of the diamond. Then just see, there are so many pearl are available nowadays. How can you check whether this pearl is highly pure or impure? There are so many faults. Pearl are available market. So just regard the spectra. Then just see for hawks, pearl, there are so many bands. That means there are some impurities. Man-made pearl. The other one pure pearl, there are one single band. So it is perfectly pure pearl. Then we see whether it is ivory or plastic. We just see, look, that's me ivory, but maybe plastic. So whether it is a plastic or ivory, you just record the Raman spectra, you can able to identify. Then you can see this is a Raman spectra of cholesterol. Okay, so you get the clear spectra. Then, you know, I told you, one of the major problem the Raman signal is the fluorescence. See, this is if we just suppose if the wavelength is, the frequency is high, you can get the fluorescence like this. So I told you, in order to reduce the fluorescence, suppose this is for beyond is just 514.5 nanometer is green light. You use the green light source, the signal is like this. See, fluorescence, because of fluorescence, there is no peak there. But if you just change the frequency, we just 785 nanometer, you get the full good Raman spectra. So fluorescence is a major problem for getting the Raman signal. So you can avoid by changing the incident radiation. If you just use NR radiation, you can avoid. Okay. So this is for fluorescence reduction. Because of the fluorescence, you will not get any Raman spectra. Then, so this is one of my compound. I published this for, I told you, The low frequency region is very important. So this is for say below 400, below 300 wave number. So in order to get the phase change for phase transition temperature, so you know the solid phase change, you can able to find it using the Raman spectra. Just increase the temperature or decrease temperature. This mode, one mode is particular mode is decreasing. So after that, that's called a softening of mode. So that temperature is called the phase transition temperature. So that means the solid phase from one phase to another phase. So that I told you this frequency, low frequency modes are very important. You can identify the free phase transition temperature. You can how the phase change from solid phase, not the liquid phase, not liquid to gas or not like solid one phase to say monoclinic or retroclinic. So the phase change can be able to identify using the Raman spectra. Okay. Now, so there are so after the invention of laser Raman spectroscopy, there are so many other developments. Surface enhanced Raman spectroscopy, resonance Raman spectroscopy, angle resolved Raman spectroscopy, Kuiper Raman spectroscopy, spontaneous Raman spectroscopy, optical tweezers Raman spectroscopy, Raman imaging. Then stimulated Raman spectroscopy, spatially offset Raman spectroscopy, coherent anti-Stokes Raman spectroscopy, Raman optical activity, transmission Raman, inverse Raman spectroscopy, tip enhanced Raman spectroscopy, surface polariton enhanced Raman scattering, standoff resolve remote Raman, then confocal Raman. There are so many developments after that. So after the development of Raman spectroscopy, so there are so many developments are there. I'll just explain simple, little bit, not all. Okay, you know resonance. I told you resonance Raman. So when an electromagnetic radiation, so then what are the advantages? I just showed what are advantages. The advantage is so even a very small trace quantity, about 10 to the minus 6 to 10 to the minus molar ratio, very small trace, you can able to record the good Raman signal. That is advantage of this resonance Raman. So the resonance Raman is you have to give the energy is equal to the difference between the two electronic layers or above. Okay. Now the other thing I just show some spectra. So here see CS4, MO2, CL6, CL8, one compound. So they have just show the resonance spectra. So the thing is, in addition to fundamental, there are some overtone bands, some combination bands. You can able to get it from the resonance Raman. You know, overtone fundamental means 0 to 1 transition. Overtone means 0 to say 2. That is first overtone. 0 to 3 second overtone. So different overtone related. Then in addition to that, some combination bands. So that also you can get it from the. So the advantage is even a small trace quantity of the sample, you can get the good Raman signal. Then see this is the resonant Raman spectra of far frame. Good Raman signal. Okay. Then what is stimulated Raman scattering? See, normally we use the continuous wave laser. So the electric field strength of the continuous wave laser of the order of say 10 to the 4 volt per meter. We know that while you do in the say simple pendulum experiment, the teachers are asked to do the vibration is small. No, don't oscillate so much. So you have to oscillate small in order to avoid the non-linear term, because then only you can put sin theta equal to theta. Otherwise, there are other additional terms comes. So here we just radiate the electric field, high electric field. The more you can, in addition to that, linear terms, some additional terms of that. So because this is a non-linear Raman. So if you just give the electric field strength of the order of 10 to the 9 volt per centimeter, you can get. So normally the Raman signal is nu 0 minus nu m. So in addition to that, you can get nu 0 minus 2 nu m, nu 0 minus 3 nu m. That is nu 0 minus n nu m. That is you can get number of bands. So that is a stimulated Raman scattering. Then coherence anti-Stokes Raman scattering. Normally, I told you the Stokes lines are more intense. So normally we used to record the Stokes line. So here, you can get the more intense in the anti-Stokes lines also. So here we are using a 2 pump laser and probe laser. So nu 1 and nu 2. So you are fixing one laser wavelength nu 1, The other frequency, you have tuned the frequency. So that nu1 minus nu2 is equal to nu-m. So in that case, so nu1 minus nu1 plus nu2, that is 2 nu1 minus nu2 and then the frequency. Okay. So you'll get 2 nu1 minus nu2. So because nu2 is equal to nu1 minus nu-m, the thing is you will get nu1 plus nu-m. The output will be, so the four-way mixing, the output will be nu1 plus nu-m. You'll get the good Raman signal. That is Stokes Raman. Normally, so anti-Stokes, because why you have anti-Stokes is nu0 minus nu-m is Stokes line, nu0 plus nu-m and anti-Stokes line. So here you get the Raman signal with nu0 plus nu1. What is the incident frequency? Nu1 plus nu-m. So that signal in the more intense. So it is called coherent anti-Stokes Raman scattering. Because you are using a sample, you are using a one source fixed, other source varied. You will get the output will be nu1 plus nu-m. Nu is a Raman line. So that this will be nu1 plus nu-m is a anti-Stokes line. So it will go good intensity line. So this is coherent anti-Stokes Raman scattering. Then hyper Raman. So this normally the Rayleigh line will be nu0, it's a Rayleigh frequency. You'll get 2 nu0 plus or minus nu-m. Okay. 3 nu0. You'll get only for the ordinary Raman, you'll get Rayleigh line is nu0. In the case of hyper Rayleigh, nu0, 2 nu0, 3 nu0, that way it gets. Okay, that is hyper Raman. Then confocal, even a small sample in a cell, you can able to record the Raman spectra. I'll just show you some of the signal. So this is a confocal aperture. So the Raman spectra for this, the pollen grain. So this is, I'll just show you. This is the mapping the drug tablets. You know, drug, there are different coatings are there. Okay. So you can different layer, you can get the different Raman lines. Then, so the different layer with different Raman signals. Then, Vikram, sir? I can finish now. Okay, 50 minutes. Okay. Okay. Say the different layers, you get the Raman spectra. Okay. Then tissue, you get the different spectra, you can see. So here, so whether it is normal artery, so different region you'll get the different spectra. So that's, you can even a very sensitive method. You want to see the spectra for the dead blood corpuscles, RBC cell. Okay. So this is host cells, RBC. Then, so this is advantages. This is for in vivo Raman system. It's a probe. So this can be take it anywhere. You can in vivo you can measure. So these are recent techniques developments for this Raman spectrometer. So using a fiber probe, just like endoscopy, you can just place it inside. It's a non-destructive testing method. So you can place it anywhere, get it, you can be able to find out the change in the spectra. You can vary what are the changes. So this method is normally used for the early checking of the cancer. Thus, in vivo Raman spectrometers, what is they are using. So live cell imaging. Now, this is a surface enhanced Raman scattering is when the molecule is allowed to inside a nanoparticles, a metal particle, either gold or silver. You can, the signal is increased about 10⁵ to 10⁶ order. Normally, Raman signals are weak. When the molecule is allowed to absorb on some metals, the intensity increase about, say, 10⁵ to 10⁶ times. Because you can use this a smaller quantity of sample, even 10 to the power 3 to 10 to the power 10 to the power minus 3 or 10 to the power minus 4 or 10 to the power minus 6, some millimolar ratio sample, that will get the good Raman signals. So there is a advantage of the source. Okay. And just see the advantages can be used in solids, liquids, and gases. No sample preparation is needed. It's a non-destructive, non-invasive, works in situ or in vitro. No vacuum needed. So works under a wide range of conditions, even a temperature and pressure. Can use down fiber optic cables for remote sampling. Very small, the sample is very small concentration, that is 10 to the power minus millimolar or micromolar sample is enough. Extremely high spatial resolution. So these are the advantage. Okay. Now, just see, there are two methods. One is, see, we know P equal to alpha E. So for the mechanism, there are two types of mechanism. One is for the source, one is electromagnetic enhancement, the other one is chemical enhancement. Okay, there are two methods normally used for this enhancement mechanism for the surface enhanced Raman scattering. Okay, so one is electromagnetic enhancement, the other one is a chemical enhancement for the charge transfer. So GOMO to LUMO, there is higher occupied, lowest, highest occupied, unoccupied molecular orbital to lowest unoccupied molecular orbital. That's a charge transfer. So there are two, one chemical enhancement, the other one is electromagnetic enhancement. So these are so many applications are there. I will not explain in detail. Okay, I'll just show you one thing. See, this is one protein compound. So we have just recorded the source spectra of different concentration. So this is normally in black line is normal Raman. Then black, say red is 10 to the power 3 molar ratio. Green is 10 to the power 4, minus 4. So this blue one is 10 to the power minus 5 molar ratio. Very small concentration, you get the good Raman signal. See, ordinary Raman has very small signal, so different. Even the concentration is very small, you get the good Raman signal. So this molecule is allowed to absorb the molecule gold particle. Okay, so this one is a theoretical one. What will get is, so this is a gold particle, first red one, this is a black. The molecule is allowed to absorb the gold nanoparticle, about particle size about say 10 to 20 nanometer size. So this red line is a gold particle, then it is allowed to absorb, this phenotone is allowed to absorb on the gold particle, you get the good Raman signal. Okay, I'll just show you the method. See here, what will happen is, see here, so the red curve is, that yellow color is a gold particle. The molecule is allowed to absorb on the surface. Since it's a nanoside, so when it is easily to penetrate the cancer cells. So that will interact with the cancer cells. So that way you can record the Raman imaging. Okay, so you'll get the Raman spectra here. So this is a molecule. This is a gold particle. The molecule is allowed to absorb over the gold particle. It will be bonded with the surface. So that will interact because of it. So interact with the laser, that will easily penetrate into the, say, because of the particles are very small, that will enter in the cell. So that will interact with the cancer cells, that will kill. So this, if you just record the Raman imaging, see here, you can size the 10 micrometer. That means if the cell size, normal cell size is much higher than this one. In this way you can, that the cell is shrinkage means there is a apoptotic cell, damage cell. So when you just find out from the Raman imaging whether the cell is malignant, you can able to detect. When just you administer medicine, the size whether it changes in occurs, that you can also monitor. So this is a method, is a non-destructive method, no painful method, simple method. So in that way, they are going to detect the early detection of early cancer. So the source is they are developing a new small instrument for this. Actually, the clinical trial is also going on in Germany. The trial is also going on for the early detection of cancer because the non-destructive testing, non-invasive, not painful. Otherwise, when you know the cancer patients are very painful, but with the chemo, there are so many other cells are also damaged. There are hair fall, so painful. So there are so many problems. But if you just administer the medicine, whether there's changes, you can able to find, say, whether the developments are there, whether cells are damaged, gaining, say, they improving, so that you can able to find out the even suspect. Okay, so these are the advantages. So it's a recent development. Okay, now, so this is a single molecule detection. So this serves Raman, it can be even a single molecule can be detected using this technique. Now this is a tip enhanced Raman. It's a recent technique, advancements. A small sample, can place it here, can get the good Raman spectra. Okay. So it's a sensitive down to single molecule level and holds some promise for bioanalysis applications. So this tip enhanced Raman scattering. Okay, spectroscopy. Now, so, okay, thank you. Thank you for your attention. If you have any doubt, please ask, or you can ask me later. Okay. Thank you. Thank you for your nice attention.
Thank you, sir. Here we move to the next section, which will be handled by Dr. Bindusar Sahu, Associate Professor at School of Physics, Indian Institute of Science Education and Research. I'm profoundly delighted that I would take this opportunity to introduce Sir on behalf of the whole department. It is a matter of great privilege that we today celebrating a program in part with National Science Day and that we can be a part of such a prestigious class.
നമ്മൾ ബ്രേക്ക് എടുക്കുന്നില്ല, കണ്ടിന്യൂ ചെയ്യാണ്. നമുക്ക് ഇന്ന് ഒരു സ്പെഷ്യൽ ഗസ്റ്റ് ഉണ്ട്. നിങ്ങളെല്ലാവരും പരിചയപ്പെട്ടോ എന്ന് അറിഞ്ഞൂടാ. ദിസ് ഇസ് ഡോക്ടർ മബ്ദ സാഹു ആൻഡ് ഹെർ ക്ലോസ് ഫ്രണ്ട് ഫ്രം ഐസർ, ഡോക്ടർ ബിൻസാർ. ആൻഡ് കുറച്ച് സമയം എന്ന് വെച്ചാൽ പി പി ടി ഒന്ന് അപ്പുറത്തോട്ട് മാറ്റാനുള്ളൊരു സമയം ഞാൻ നിങ്ങളോട് സംസാരിക്കാമെന്ന് വിചാരിക്കുകയാണ്. ഞാൻ പറയുന്നത് ഇത് കഴിഞ്ഞ് നിങ്ങൾക്ക് അധ്യാപകരായിട്ട് സംസാരിക്കാൻ ഒരു അവസരം ഉണ്ടാകുന്നതാണ്. യു ക്യാൻ ഗോ ആൻഡ് ടോക്ക് ടു ദം ആൻഡ് ഡിസ്കസ് വിത്ത് ദം വാട്ട് ഈസ് ബീൻ ഡിസ്കസ് ഇൻ ദ സ്ലൈഡ്. പേഴ്സണലി ചെന്ന് മിണ്ടണം, സംസാരിക്കണം. ജോസാറ് നല്ലൊരു അവസരം തന്നിട്ടുണ്ട് ഇത് കഴിഞ്ഞ് പോയി നിങ്ങൾ സംസാരിക്കാനായിട്ട്. അപ്പം നമ്മുടെ ഡിപ്പാർട്ട്മെന്റ് ഓഫ് ഫിസിക്സിൽ ഇവരെല്ലാവരും ഉണ്ടാവും. അപ്പം നിങ്ങൾക്ക് എപ്പോൾ വേണമെങ്കിലും വന്ന് സംസാരിക്കാവുന്നതാണ്. ഈ 3 ദിവസം എന്നോടും സംസാരിക്കുക, അതുപോലെ ഡിപ്പാർട്ട്മെന്റിലുള്ള എല്ലാ അധ്യാപകരുമായിട്ടൊക്കെ ഒന്ന് ഡിസ്കസ് ചെയ്യുക. വി വാണ്ട് ടു നോ യു, വി വാണ്ട് ടു അറ്റ്ലീസ്റ്റ് നോ യുവർ നെയിംസ്. സോ വളരെ അൺഒഫീഷ്യലായിട്ട് തന്നെ ഞാൻ സാറിനെ വിളിക്കുകയാണ് ടോക്ക് ഡെലിവർ ചെയ്യാനായിട്ട്. സോ 2 minutes. I will just call upon Dr. Mamda Sahu to introduce the speaker.
Thank you, Dr. Sibi. For actually, it was very short notice. We arranged everything, and I think it's perfect and right time. So we are here. So first of all, let me thank Dr. Bindu sir for accepting our invitation and willing to give a talk in such a short notice. So thank you, Bindu sir. So he will be talking about today. He will be talking about the theory of fundamental force. It's not actually force; it is force. So the topic looks very interesting. So we all are very much interested and looking forward to hear from him. So before proceeding further, let me give a brief introduction about Dr. Bindushar. He is presently working as an assistant professor, associate professor in School of Physics, Indian Institute of Science, Education and Research, Thiruvananthapuram. He did his integrated masters from Indian Institute of Science, Kharagpur, and then he did his PhD from Harishchandra Research Institute, which is shortly named as HRI Allahabad. He joined ISER Thiruvananthapuram in the year 2013. Prior to his joining at ISER Thiruvananthapuram, he has done several postdoctoral research in various institutes like Abdus Salam International Center for Theoretical Physics, Trieste, Italy, Institute for Theoretical Physics, Utrecht University, Utrecht, Netherlands, and National Institute for Subatomic Physics, which is shortly named as NIKHEF, Amsterdam, Netherlands. So he did PhD in the mainly broadly in the area of string theory or high energy physics, and he did his PhD with Professor Ashok Sen, who is a giant actually, or you can say he's a pioneer in the area of string theory in the whole world. So I must introduce that. And I think at present, anyway, we have already talked. So at present, he is in ISER Thiruvananthapuram. And as far as his research is concerned, so he has been extensively working in the broad in the areas of conformal supergravity, supersymmetry, and so on. So broadly in string theory. So as we know that this string theory and high energy physics is an exciting as well as emerging areas in physics. So I hope today's talk will be very much helpful as well as informative to all of our students. And also I request all the students, so please interact with the speaker after the talk. Take the advantage of his talk. Even if you can also ask his email ID and later on you can email. And I think these things already was mentioned, our HOD. So with this short introduction, I invite Dr. Bindu sir to deliver his talk. So Bindu sir, please.
Thank you. Thank you very much. Okay. Good morning, everyone. And thank you, Mamta, for the nice introduction. And thank you, the Department of Physics and the students for inviting me here and giving me an opportunity to speak with you and interact with you. Okay, so I hope we will have a nice interaction. Okay, so today I am going to talk about, I'll tell you a story. I will not bore you with any technical stuff. Okay, and the story is of the fundamental force. It's force, F-O-U-R-S, which also rhymes with force, F-O-R-C-E. Okay, I hope as kids you have studied the story of the famous five. Okay, the adventures of the famous five. Okay, so this is somewhat like that, the story of the fundamental force. Okay, so what are these fundamental force? They're actually the fundamental forces that govern our nature. So what are these fundamental forces? Okay, so first, the most prominent fundamental force that we see around us. Okay, I mean, starting from our childhood. Okay, before we understand any other force, this is one force that we understand. I mean, we see, we don't understand, we still don't understand this force well, and that is gravity. Okay, what does gravity do? Okay, okay, of course, it makes the apple fall from the tree. Okay, and it also binds your solar system, right? All the planets, asteroids, everything inside the solar system is it's bound by the gravitational force. Okay. Okay, so that is the most prominent force that we see around us. It is the most observed force, but it's the least understood force. And I will tell you why it is the least understood force among all the four forces. Okay, so the next one. Okay, so the next force after gravity, which is more commonly observed, is the electromagnetic force, right? So maybe as a child you won't understand or see these forces so prominently, but once you grow up a little bit, you tend to understand that there is something called electromagnetic force. Okay, electric force and magnetic force. Okay, the force that drives the electric current inside your home. Okay, that is also somewhat common, like gravitational force. Okay, and what does it do? It binds the atom, right? The electron and the proton inside the atom. Okay, they are bound by electromagnetic force. Electromagnetic force is what keeps them bound together. It doesn't fall apart, right? Okay, so this is the second most prominent force. The other two forces are not so prominent. Okay, this is the strong interaction. Okay, strong interaction is not something that you commonly observe in your day-to-day life. Okay, but when you think about it, when the structure of the atom was discovered, bit by bit. Okay, first electron was discovered, and then the nucleus was discovered, and then it was discovered that inside nucleus is not a fundamental particle. Inside you have protons and neutrons. Okay, but protons and neutrons, okay, they have some charges, right? Proton has positive charge, neutron has neutral charge. So if there are some protons inside a nucleus, okay, and they have equal charges, and we know that equal charges repel, right? So if you have two protons inside a nucleus or three protons inside a nucleus, and they all repel each other because of electromagnetic repulsion, because they have equal charges, okay, so they should fall apart. So what is it that is binding them together inside the nucleus? Okay, and that is something which overcomes the electromagnetic repulsion inside the nucleus. Okay, and that is the strong interaction. Okay, so the strong interaction is more prominent when your particles are, whichever particles experience a strong interaction, which is that whenever they're close to each other, it becomes more prominent, and when they're far away from each other, it becomes less prominent. So when you take two protons far away from each other, then the most prominent force that is affecting them is the electromagnetic force. But when they come closer to each other at the nuclear scale, it is a strong interaction, okay, which binds them together. Okay, it's a strong interaction between protons and neutrons, between protons and neutrons that binds them together inside the nucleus. Okay, so it is not so when I say it's more prominent when they're close to each other, in technical term, you would say that they're short range interactions. They are not long range interaction like the electromagnetic interaction or gravitational interaction. Okay, so that is why you don't commonly observe them in your day-to-day life. Okay, you don't see particles experiencing strong interaction around you. Okay, they are more prominent inside a nucleus. Okay. Yeah. So the next one is the weak interaction. Okay, it is kind of different from your strong interaction and electromagnetic. Yeah, it's kind of different from your strong interaction and electromagnetic interaction and gravitational interaction, in the sense that this interaction, it's an interaction between particles, but this interaction tends for, it's responsible for decay of particles. Okay, we know, we have studied in our physics courses that there is that heavier nucleus decay to lighter nuclei by emitting what is called the beta particle. Okay, it's called the beta decay. Okay, so some interaction is driving that decay. Okay, and that interaction is a weak interaction. Okay, okay, so it's weak interaction. It's called weak interaction because its magnitude is weaker than the strong interaction. Right? There is something. No, there is some. You can measure the strength of the interaction. Okay, and weak interaction has weaker strength than the strong interaction. Okay, that is why it's called weak interaction. And it's basically responsible for your nuclear decay. Okay? So these are roughly the 4 fundamental interactions that we see in our nature that governs everything in our nature: electromagnetic, gravitational, strong, and weak. These are the 4 interactions that governs everything in our nature. Okay, and classically we understand. I mean, classically, of course, gravitational and electromagnetic interaction we understand. Strong and weak interaction, as I said, they are observed at a shorter scale. They are short range interaction. So you don't have a classical description of them. Okay, it's more, I mean, you have to use quantum theory to understand these interactions. Okay? And in quantum theory, you also, at shorter scales also, you for electromagnetic and gravitational interaction, you need a quantum theory. Okay, and in quantum theory, these interactions are basically mediated by particles. Okay, so these are what are called, Feynman diagrams. Okay, I'll not go into the details of the Feynman diagram. I will rather explain these as some kind of cartoon. Okay, so how electromagnetic force is understood in quantum theory is that, suppose you have 2 electrons which are experiencing electromagnetic interaction. What actually in classically how you understand them? Classically, you understand that one electron creates an electromagnetic field around itself, and that electromagnetic field that it creates, the other electron responds to that electromagnetic field, and that is how they interact with each other. That is how you understand classical electromagnetic interaction. And in quantum theory, how you understand these interactions is that this electron emits a photon, okay, and recoils. Okay, and that photon that is emitted, okay, it is absorbed by the other electron and it recoils. Okay, so it is like, this is like a cartoon way of explaining this Feynman diagram. Okay, I mean, to understand Feynman diagram in more details, you have to go into the mathematical details of what is called quantum field theory, which is the framework for understanding these interactions at the quantum level. Okay, but I'm trying to explain this at a cartoon, as a cartoon. So you have an electron which emits a photon, recoils, and the other electron basically absorbs the electron and recoils. That is how you see these electrons interacting by electromagnetic interaction. So in quantum theory, this is how most interactions are pictured. Okay, they are the interactions take place via exchange of particles. Okay, so electromagnetic interaction is taken place by the exchange of a photon, okay, which is the quanta of the electromagnetic radiation. Okay, weak interaction is taking place by the exchange of what is called a W boson.